I'm Adam from RFOXiA, from our real lab. Today we are answering why a gyroscope and an accelerometer are each on their own scientifically unreliable for real motion applications and what sensor fusion actually means in practice. Enjoy our new soundtrack at the end of the video. Let me start with something the component datasheet will not tell you. A gyroscope measures angular velocity. That is all it does. It tells you how fast you are rotating around an axis. It does not tell you where you are pointing. It does not tell you your absolute orientation in space. It gives you rate of rotation, and then you are expected to integrate that over time to get an angle. And that is where the problem starts. Integration accumulates error. Every tiny measurement noise, every small bias in the sensor, every quantization artifact from your ADC, all of it gets added up over time. The technical term is drift. After a few seconds, your integrated angle is wrong. After a few minutes, it is embarrassingly wrong. After an hour, it has no relationship to physical reality. This is not a defect. It is the physics of how the measurement works. A gyroscope is a derivative sensor. You are working backwards from a rate to a position, and that process is lossy by definition. Now let us talk about the accelerometer. An accelerometer measures force. Specifically, it measures the sum of all linear accelerations acting on it, including gravity. When the sensor is sitting still on a flat surface, it reads 1g pointing downward. That reading is stable and accurate and can tell you the sensor's tilt relative to gravity. This is useful, but the moment the sensor starts moving, the moment there is any actual linear acceleration in the system, the measurement becomes ambiguous. The sensor cannot distinguish between gravitational pull and motion-induced acceleration. They add together in the measurement. If your drone is accelerating forward, the accelerometer sees a combination of gravity and that forward force, and it cannot separate them. You cannot derive reliable orientation from an accelerometer that is on a moving platform. So now you have two sensors. One that knows rotation rate but accumulates error over time. One that knows the gravity vector but gets confused by motion. Neither of them can do the job alone. That is not a coincidence. That is why they are always paired. The technique for combining them is called sensor fusion. The most common implementation is a complementary filter or a Kalman filter. The logic is straightforward once you understand the failure modes of each sensor. The gyroscope is good at short-term, high-frequency angular changes. It responds quickly and accurately to fast motion. The accelerometer is good at long-term, low-frequency orientation correction because gravity is always there and always pointing the same direction. So you use the gyroscope for moment-to-moment rotation tracking, and you use the accelerometer to periodically correct the drift that the gyroscope accumulates. The complementary filter is literally just a weighted average. You trust the gyroscope for rapid changes, you trust the accelerometer for slow drift correction, and you blend them with a tunable coefficient. It sounds almost too simple. But it works because you are exploiting the specific error characteristics of each sensor. You are compensating for one sensor's weakness with the other sensor's strength. A Kalman filter does the same thing with more mathematical rigor. It maintains a probabilistic model of the system state and updates it based on the noise characteristics of each sensor. It gives you better results in complex dynamics but requires more tuning and computational overhead. Now add the magnetometer. Gyroscope and accelerometer fusion gives you pitch and roll reliably. It does not give you yaw. Yaw is rotation around the vertical axis and heading. The accelerometer cannot help with yaw because gravity has no horizontal component to reference. The gyroscope can track yaw rate, but it will drift just like it drifts on the other axis. A magnetometer measures the local magnetic field vector. If you are not near large ferromagnetic objects, that vector points toward magnetic north, and it gives you an absolute heading reference. So the magnetometer corrects yaw drift the way the accelerometer corrects pitch and roll drift. All three sensors together, accelerometer, gyroscope, magnetometer, give you a full 9-axis orientation solution that is stable over time and resistant to drift. This is what people mean when they say 9-axis IMU. This is why the BMI 270 from Bosch pairs accelerometer and gyroscope on a single die. Tight integration reduces the timing error between measurements. When you are fusing sensor data, synchronization matters. If your gyroscope measurement is from a different moment than your accelerometer measurement, the fusion math is working with inconsistent data. Co-located sensors with a shared timing reference reduce that problem significantly. The air pressure sensor adds a barometric altitude reading. Not high precision absolute altitude, but changes in altitude that are reliable and fast. Combined with GNSS for absolute position and the IMU for orientation, pressure altitude fills in the vertical accuracy gaps that GPS alone cannot provide at high update rates. The humidity and temperature sensors extend the environmental picture. Temperature compensation is particularly important because MEMS sensors, the inertial sensors, have temperature-dependent bias. If you are flying a drone from a warm ground environment into cold air at altitude, the sensor characteristics shift. Having an onboard temperature reference gives your firmware the data it needs to apply compensation. And the air quality sensor is the outlier in this group. It does not affect the motion math. It is there because if you are deploying a sensor package outdoors, in a drone or a fixed station, air quality is frequently the most valuable data in the set. The motion sensors tell you where the platform is and how it is moved. So that is why sensor fusion exists and why the specific chips on this module were selected. Now let me show you what it actually looks like as a piece of hardware. This is the full sensor array in one module: accelerometer, gyroscope, magnetometer, temperature, air pressure, humidity, and air quality, all on a single board. 7 sensors that individually would require 7 separate procurement decisions, 7 separate layouts, and 7 separate I2C implementations. This board is what sensor fusion looks like before you write a single line of code. The motion sensors and the environmental sensors serve fundamentally different roles, and both are represented here. The BMI 270 handles the high-frequency, angular and linear data your fusion algorithm depends on. The environmental sensors provide the slower, longer horizon data for altitude correction, temperature compensation, and real-world context. Neither group is optional if you want a complete picture. The specific chips on this board were not chosen arbitrarily. The BMI 270 from Bosch SensorTech is a co-located accelerometer and gyroscope, which means synchronized timing. The TM-AGI 5273 from Texas Instruments handles magnetometry. ST Micro provides the pressure sensor. MEMS Vision handles humidity and temperature. Renesas covers air quality. These are production-grade components, not evaluation tier alternatives. All 7 sensors share a single I2C bus with dedicated addresses. This was a deliberate layout decision. Shared bus means one set of pull-up resistors, one pair of signal lines, one protocol to implement in firmware. Each sensor has its own address, so there are no collisions and no arbitration overhead. The wiring complexity you would normally have across 7 separate modules is eliminated at the board level. The module is 24 by 18 millimeters. That is smaller than a postage stamp. At that size, it fits in a drone frame without compromising center of gravity, on a wearable without adding bulk, and in an IoT enclosure without requiring a custom chassis. Compact form factor was a constraint, not an afterthought. Every component placement on this board was made to hit that dimension. Real-time environmental data means the readings are available continuously, not on a pull request cycle that introduces latency. When your platform is moving and the conditions around it are changing, you need data that reflects now, not 500 milliseconds ago. The sensor module streams all 7 channels at rates appropriate for each measurement type, and your firmware consumes exactly what it needs. The application range for a module with this sensor combination is deliberately broad: drone orientation and altitude, environmental monitoring stations, robotics with spatial awareness, field research platforms, industrial IoT with air quality compliance requirements, wearable motion capture, data network nodes earning daily rewards through verified sensor streams, one board, one integration effort, many deployment contexts. Component. The reason I chose these specific chips for the sensors module, the Bosch BMI 270, the Texas Instruments magnetometer, the ST Micro pressure sensor, the MEMS Vision humidity and temperature sensor, the Renesas air quality chip, is that each one represents the current state of the art in its measurement category at a form factor that fits on a 24 by 18 millimeter board. You are not compromising on sensor quality to get integration. The integration is just engineering.
Seven signals in the dark. Every axis, every arc, the pressure dropping overhead, the temperature that overhead, the temperature that fills with dread. I feel the tilt before you fall. I read the field behind the wall. The story that the data holds, the story that the data tells. I sense what you cannot see. Magnetic heat, motion locked humidity, motion locked in real-time streams. The world to code, not what it's. 7 sensors, one board, one truth. Every shift and every move, the invisible made visible night, equality through industrial air. 3-axis matter to where. Humidity shifts before the storm. Pressure maps the rising norm. All 7 running, all in sync, faster than you stop to think. I sense what you cannot see.